working with this one about probability of A and B is equal to the probability of A times the probability of B given A, which goes back to probability of B given A is equal to probability of A and B divided by probability of A. So you're kind of rearranging these things, and we're extending it here. The same fundamental idea, concept, that's what we're working with. Bayes' theorem, okay? Given two events, A and B, and a probability of B greater than 0, it can be shown that probability of A given B is equal to probability of B and A divided by probability of B. Okay, that's nothing new. No big surprises there. But here's where we get a little surprise. Well, you take that top part, what's the probability of B and A? Well, that turns out to be, just by definition of conditional, that's the same thing as the top part. Probability of B and A is equal to probability of B given A times the probability of A. So you're substituting in. And the reason this is, you do this and where Bayes came from is that you think, again, you may have some probabilities. You may have some pieces of data that you can work with to go figure out certain probabilities. And you're using those to derive other probabilities. So you work with what you have to extend what you know and develop some other probabilities. So that's the essence of what Bayes is about. Kind of turn your head sideways and like, what are they doing there? But it's pretty useful stuff, actually. Okay, statistics. Oh, this is a morbid, this is a pretty dreary example, but here we go. Statistics show that 70% of all men have some form of prostate cancer. The PSA test will show positive 90% of the time for afflicted men and 10% of the time for healthy men. What is the probability that a man who has tested positive truly does have prostate cancer? And, I don't know about you, but, this is kind of what you run into, right? You can have false positive, you can have false negative. This is a lot of the medical community looks at that very carefully, and this kind of work is very common. So, again, you have a test that 70% of all men have some form of prostate cancer. There's a test that shows positive 90% of the time for men who are afflicted. This is a good thing. It's come back with the right result. And 10% of the time, it comes positive for healthy men. That's a bad thing. That's a mistake, right? So this is the data you're given. So what's the probability that a man who is tested positive does have prostate cancer? So let A be the event that a man has prostate cancer, and B the event that a PSA test is positive. Then the question is to find what's the probability of A, he has prostate cancer, given B that the test came back positive. So probability of A is equal to 0.7. We were told that. By the complement rule, we know that somebody either has the cancer or they don't. So 1 minus 0.7 gives the probability that he doesn't have prostate cancer. Probability of B given A, probability that the test came back positive given someone has the cancer, that's 0.9. We were also given that information. We were told that information. What's the probability of a positive test given that they don't have the cancer? That was 0.1. So now we say, well, what's the probability of A and B? And we can determine that using probability of B given A, which is 0.9, times the probability of A, that's 0.7. So we have a probability of B and A is equal to 0.63. Probability of B is that there's a negative, what's the probability that the test is positive? Probability of a positive test is equal to the probability, a test is either going to be, a test comes back positive for the people that have cancer, and the test comes back positive for the people that don't have cancer. So we look at both pieces of that and say, okay, probability of B and A is probability B given A times the probability of A. That's what we just figured out, the 0.63. Plus probability of B given not, they don't have the cancer, times the probability they don't have the cancer. Probability of B given not A is 0.1 times the probability that they don't have the cancer, 0.7. So that probability that the test comes back positive is equal to 0.66. I know, I have to guess your head is going, what in the world? This is how Bayes is. I remember doing it as an undergrad going, oh my gosh, this is twisting your head sideways. But yeah, indeed. So you're basically working with the information you have, working with these different rules and applying them, and then deriving and saying, what's the probability that a person has cancer given the test came back positive? And that's equal to the probability of B and A divided by the probability of B, which turns out to be a 0.9545 probability. Probability that somebody, so again, probability that somebody has cancer given the test came back positive is 0.9545. So that's a pretty high percentage chance, which if you are the pharmaceutical, the manufacturer of that particular test, you know, that's part of where you go. You go, well, is that high enough? Is there somewhere, you know, is that sufficient to release this as a test that the medical community could use and so forth? Okay, learning checkpoint 14. A retailer receives 75% of its batteries from factory A and 25% from factory B. The percentage of defects produced at factory A and B are known to be 1% and 2% respectively. A customer has just bought a battery randomly from the retailer. Now here's the hardest thing about Bayes. You really got to think about, well, what information was I given, and structuring it. Saying, okay, what is my A? What is my, in this case, you got to, you know, what's your event? Percentage of defects. The customer has just bought a battery randomly from the retailer. What is the probability that the battery is defective? So you've got to set up and say, what are your events? How are you going to label them? And then the next is, what is the data that you're given here? What probabilities are you given as part of, you know, background? So that you can then go figure out the answers to what's the probability that the battery is defective. If the battery you bought is defective, what is the probability that it came from factory A? Okay, so again, you have the solution to this in the probability learning checkpoint slides. Okay, next piece, and there's one more learning checkpoint on this, but basically it's the extension of Bayes' theorem. And it's saying that you are able to actually figure out different conditional probabilities based on other ones. And I'm not even going to go through this hairy thing. There is an example of this, so if you want to go through it, we can do this when we're face-to-face as well. Don't cramp up and, you know, freak out on me here. We can go back and do this while we're face-to-face because it is fairly complicated. But it is fundamentally, I care more that you get to understanding how this operates, the basic, the mini version of Bayes' theorem, and have a feel for what that's about. Again, don't get too wrapped up in, this is the first wave. When we're face-to-face in class, we'll go through a lot of different examples and work on exercises so that you get the practice and get a really firm, hopefully, appreciation for these concepts. Okay, so this actually wraps up the end of our Introduction to Probability series or group of sessions, and we will see you next time around as we go to the next chapter.